Alright, so for the third part of the project, we have to the other file there is I was testing how to make this work, and so now I'm going to remake it and make the viscous one as well, or the inviscid one as well. So for the first part, for the third part, sorry, which we will have flow simulation of airflow over a semicircular cylinder with a radius of 10 meters. First have to put in the fluent and make it open. Here, I'm not sure that the size of the rectangle matters a lot. I figured I'd make it be like twice as big as the circle, and it worked. So I'm going to continue doing that. So if the circle has a 10 radius, we do it 30 meters, and we do 60 meters length, because that way there will be 20 meters to each side of the circle, of the semicircle. Then we can add circle. And if we come here and we do an horizontal measure there, we can make sure that it is 30 meters away from the center, which should mean it's centralized. And for the radius, then that's going to be a 20-meter circle with 20 meters to each side. Then we're going to modify and trim, and we destroy this stuff. And that way we are going to be able to model over that. Modeling concept surfaces from sketches, and we select all of these. Apply. Generate. That's that. So we can close off this. I'm going to mesh. First thing here is we do our different walls. We have to name all of them. So we have the inlet, and we do that by clicking the edge and pressing N to open this selection name. The outlet, we have the walls, and we can select all of these walls by control clicking. And then we should name the cylinder walls separately for our calculations. And you can see that they're all here now: inlet, outlet, wall, cylinder wall. Then for meshing, we can. The way I figured to do this that worked was by having. No, that is not what I want. Edge. You can select the bottom 3 edges. Convert divisions into 300. And then the other 3 edges. number of divisions and do 200. And then refinement. And do 3. And then I'll click generate, and it's going to be a bit, so I'm gonna pause the video. Alright, we have finished the meshing process. So that's what that thing that I put on at the 300 on the bottom, 200 on the top, and the refinement of 3 turns out as. And I think that's pretty decent, so we click updates to make sure that that goes back to the actual fluent up here. We can close that. We'll take a moment to understand what's going on. There it is. Then we go to setup. We should click double precision. I have access to all 16 server processes, so I'm gonna have them all open, because that just makes the simulation go faster. Right, here it is. So we have a couple guidelines for this. First things first, I will start with a viscous one. I'm just going to live with K omega because the assignment says that any turbulent model will do. For our fluid, the assignment says to use 1.2 for the density, so I'm going to just change that. It doesn't say anything about the viscosity, so I'm going to keep it as is. Check. Oh, I clicked the wrong button to leave. Change. For our boundary conditions, we have to give the inlet a velocity. Yep, that's that. And I believe we can just run. Yes. So initialization and run calculation. I just put 200 iterations. Oh, right, I have to change the residuals. Just add a couple zeros to make sure that it gets to a decent certainty that it has found the correct solution. And I do 300 iterations just because it will resolve before that. Because it will resolve whenever it reaches the desired certainty, but if I put 300 there, it means that it gets. Alright, this one didn't resolve, so doing 300 just to make sure it develops as far as possible, but I don't think it will ever resolve, but the certainties are small enough at this point that it should be fine. In fact, if I hadn't changed towards more certainty for the continuity, it would be a valid answer as far as the program is concerned, so I increase the amount of certainty that I'm requiring out of it, and it can't always give me that. But this should be fine. So for the actual assignment, it wants the velocity contour and the pressure contour. So velocity contour, velocity, and we want all of it. Save display. It's that. Then we can make a new contour. Now I'm gonna make this nice because I will then, after finishing the video, come in here and record all of this data. We need pressure contour, so static pressure. There it is. Do new, do dynamic pressure. Which is basically the opposite of the static pressure, which makes sense given the pressure shouldn't be changing. And we can also do total pressure, which is the addition of both of them. And we can see that it does in fact change because, well, it doesn't totally change. This should be the same as this. But here there's less pressure because of flow separation. Let's see, we can look at the console, and yeah, so here the pressure is in between this 760 and 770, and here it's around the same thing. But here it's very different because of flow separation on the cylinder. Yeah, so that are the velocity and the pressures. Then we need to plot the pressure coefficient and velocity distribution over the surface of the cylinder. So pressure coefficient over the cylinder wall. And get this, which is to be expected, right? Starts very high at the point, this is stagnation point right here, then goes down and goes back to being normal at the end of the cylinder, to zero in fact. The other plot that we need is the velocity distribution. And when I'm actually getting this data to work with, I will write to file in order points, and then it will give me an Excel to work with. But right now, since I'm just showing it to you, velocity, magnitude on cylinder wall, and because this is a viscous, it means that the velocity on the wall is always just zero because of this low lip condition. I haven't tried the laminar circulation yet. We'll do that together in a bit, but I expect that there will be an actual velocity there that will be different. And so last thing we need is, we also need the drag and lift coefficient. And for those, I can go here. I need to get a console open. And we can print the forces on the X direction for the cylinder wall. And this should be our drag. So I copied that and I come to this spreadsheet. And I was trying this out earlier, so that's that. Drag Siemens. No, drag flow, I'm sorry. Viscous simulation. Not copy it. And we can coefficient of drag. And I was working out what the exact math was earlier. It's gonna be this because we equals E2 because it's divided by half times the pressure times the diameter of the thing we are going over times the velocity squared. So and then for the lift, we do the same thing, but it's at y equals 1, because we want the forces in the y direction. This total lift. That's that. So this is all for the viscous simulation, and then we have to do some of these steps again for the laminar, not laminar, sorry, inviscid simulation. Words are hard, and I just woke up. But yeah, so we are here, and there is a thing in Fluent where, in order for me to not have to do the geometry in the mesh again, I can do this. And basically what that is doing is it's copying my geometry and my mesh into this other one. So if I open the mesh here, it should just be the same as the other one was. And I did that by just clicking the mesh here and like holding it clicked for a couple of while I was dragging it there. Huh, why did that not work? I'm gonna pause the video and figure out why that didn't work and then continue. Okay, I figured it out. I'm not allowed to open this, I forgot that. So after that I opened this mesh, just checked that it was still all working, and then doing that gave the check marks on all of these, and I clicked update here, and that fixed this one, and so I should be good to just open the setup. And so it remembers that I want double precision and 16 silver processes, so start. And as you can see, I unfortunately do not get any of the graphs back, but that should be easy enough to do. So we go here, and we have to change our model from viscous to laminar. No, from inviscid, sorry. 30. Yeah, inviscid. And then we change the material to have a density of 1.2. And our inlet to have 25 velocity. And I will also again do the residuals, but it to be more before deciding that it works. Yeah, so initialization, initialize, and run calculation, and 100 iterations, and calculate. It will not get to as much precision as I wanted to on the continuity, but it does for the x velocity and y velocity, similarly to what happened with the viscous simulation. So I think it's good enough. So we just from this point go to our results and we do the same few graphs that we did for the other one. Static pressure, and we can see that it's a very different shape than it was in the other one. This I believe to be a simulation error, but I don't think there's anything we can do about that. It's the mesh maybe could change, but I don't think that is significant to our results. Then we have dynamic pressure. The important distinction here is the fact that the flow does go all the way around the cylinder and just continue going. I expect when we see the velocity graph, it will actually change across the geometry. And this one, the dynamic pressure, is just a mirror of the static pressure. With that point being something where the simulation got confused about something that it shouldn't change any of our results, so I'm just going to leave it as is. Because the important part is at the top right there for all of them. So those are all our contours, and I'm setting them nice like this because I want to come back through this and actually get screenshots of all of it for the report. And then we have our XY plot. So we need a pressure coefficient over the cylinder wall. And we can see that it is very different, and I think this is the part that matters, and this is the problem. This is the thing that happened that was weird that we were seeing. So I will just report all the way to 39 instead of 40. I don't think it makes a difference either way, because we can see that the lowest pressure happens right at the middle of the we have a velocity. Why are you not doing it? Let me pause the video and figure out what's not working here. Okay, that was quick. I opened the console and it says the objective team name already exists. I think it's because my contour also is just named velocity. So if I say velocity xy, that should work. Yep. And yeah, the important part is this, and this is the weirdness that we're seeing, which might be because of the laminar of the inviscid solution, given it didn't happen with the turbulent one. I'm not sure, but the important part is this. And then we have our reports and forces. And we can see this. lot less. Seed simulation, drag fluent. A lot less drag. Because I think we have only the drag due to left, I think is why we have so little drag. No, that's all it changes. And then we have a significantly larger left than we had the other time, because there's less viscosity reduces left. And then we can similarly calculate coefficient of drag, coefficient of left, and this should just do it for me. Yep. So yeah, that is all the results for, all of the fluent for part 3 of the project.